name is Zhe Wang. I'm from Rutgers University. In this video, I'm going to present my solution for the BitTiger microproject Mini-Cassandra. The Cassandra is a NoSQL distributed database. It is a Apache open source project initially developed by Facebook. It uses a basic concept of distributed hash table, the CORD protocol. Before we get into how to implement CORD, let's talk about first how or why do we need Cassandra or this type of architecture. So initially, or traditionally, database is designing a decentralized pattern, meaning there's only one logic server, central server, which stores all the data that all the user want, and if they want, they have to query this machine. And so it soon becomes the bottleneck because the power, the throughput of one machine is very limited. So then people decides to distribute the database. Well, then that involves with a question or problem of data sharding, and if, for example, in this example, people shard their data due to the different module of the system, or we can see due to the different schema of the database, but that causes imbalanced workload, right? Some machine power is wasted. Therefore, people will try to balance the load of database, and one simple solution is used, and that's a hash function, or probably just modular to distribute it, try to evenly distribute the data. As in this example, there are two databases, right? So you just mod 2 for the key of the data, and so as you can see, data 0 to 4 even numbers goes into 0, and 1 through 5 goes to the odd number, so it goes to database 1. But here's the problem, right? So if then 2 servers is not enough, you can introduce another database. Then what should you do? You have to do the rehashing. Alright, so basically you recalculate the key and to see how they fell. In this case, you mod 3 of the key, right, to see how they fell into different category. So then 2 goes to database 2, 4 go to database 1, then 3 goes to database 0, then 5 goes to database 2, then that's it, right? But what if now you want to get rid of a machine, and that you want to use that machine to do other things? How do you move, right? So you have to kind of move back to this case, and then there's another rehashing, right? So as you can see, it's problematic when you want to do reconfiguration. So people then come up with consistent hashing. Consistent hashing is similar to the previous one, right? Still, several in this case, these 4 blue dots are the 4 database server. They handle certain number of data set, but instead of you doing the hashing every time, actually they do a hash. They hash the key into a very long result, or which is actually from the number 0 to, let's say, 2 to the power of 32 minus 1, right? So then they just have a certain range that each node is gonna take. So in this case, actually, they takes all the number before it in a clockwise way, meaning 3 is going to take from 15 to 3. 8 is going to taking care of 4 to 8. 10 is going to taking care of from 9 to 10, and 14 is going to take care of 11. Alright, so as you can see, everyone is still taking care of a group of data, but then you may ask, well, then how that's better than the previous case? It is better when there are someone join or someone left. Let's say node 6 is the newly joined node, right? So in In this case, 6 is going to be responsible for 4, 5, 6. And who was responsible for that? 8, right? 8 used to be responsible for from 4 to 8. But in this case, 8 has to give 4, 5, 6 to 6. But that's it, right? So as you can see, only one operation is involved. And for node 8, 10, node 14, node 3, they didn't do anything. Alright, so that's much better than rehashing, because rehashing, you calculate all the data set. Okay, so that's how to say, a large improvement, but that's not enough, because when you are do searching or retrieval of data, right, you don't know who is taking care of what data. In that case, you have to ask all of servers. In this case, if someone asks 3 to say who has 11, 3 doesn't know. 3 will ask 6, ask 8, ask 10, and ask 14 who has 11, and 14 will reply, I have 11, here it is. So then that's an order of number of machines, of servers. That's not good enough. So people come up with the protocol which is called CORD, and it has only partial list of the server. How partial? It's log of n. Alright, so in this case, theoretically you can have in total 8 servers, right? So it has only 3 items, which is 2 to the power of 3. Alright, so that's log n. And for each item, it basically shows for this is who is taking care of 1, 1, who is taking care of 2, 3, who is taking care of 4, 0. Similarly, 3 is taking care of 2, 3 is taking care of 3, and 0 is taking care of 5. Alright, so it's a partial. And next, let's see how they actually get one data. So get one data is actually for this one example is the red one. Okay, so we want to know where is k, and we ask node 1. So node 1 will look into its table and find, I'll say, try to find the nearest one before it, which is this one. And 18 will look into its table, try to find the nearest one that's before it, which is 20. 20 will look into its table to see who is the nearest one before it, this one. And this one will look into its table, see which one is the nearest one before it, none. So it must be between me and my successor, so which is actually 26. Alright, let's do another example here. This dot line, a blue dot line. So we ask node 28 to see where's 12. It will ask its table to see who is the nearest one before it is 4. Then 4 will see who is the closest one that's before before 12. It's 9, so we ask 9. 9, who is the nearest one before 12? It's 11, so we'll ask 11 to see who is the nearest one before it. No. Oh, so it must be between me and my successor, who is 14. So just ask 14. 14 must have 12. Okay, so here's how that is. And so to do the demo, we're gonna I want to first show, actually, for what I described is just really simple 2 functions. Alright, so I suggest you to read this paper, the core paper. They have 2, but you will always get both of them when you search them. So just these 2 questions, functions, well, along with how do you form this. They call it finger table, but it's really a routing table. How do you form this routing table? Alright, and also they have certain function to be called periodically to make sure that the finger table is updated. Alright, so for the sake of time, we don't have to explain this, but basically the requirement of this project is you just implement those functions, right? So here's what I did. So I was making use of several tools. First of all, I'm using Uber's T channel, which is a protocol for doing RPC, and has library for Node.js, Python, Go, and Java. I suggest you just take a look at it. Also, I'm using Hyperbarn, which is also developed by Uber. It's used for I use it for service discovery and routing, because how do you find each other within this ring, right? And well, you can assume that they always know its address, but but this is the usual way that you have to have an infrastructure doing the service discovery. Okay, that's another tool I use. Well, that's pretty much. So basically, I start from the building the RPC and implement several this is the place that I said the function got periodically called, and those are function how to query the finger table, and how to update the finger table. So to do a demo, let me first show you what I'm going to show. What I'm going to show is, first, let's see, there's only node node 0, node 1, and node 3. So their routing table should be looking like this: 130, 330, and 000. Alright, so that's our initial state. Let me do that. Actually, I have the Hyperbarn running. Alright, you have. So I'm printing out predecessor, successor, and its finger table. Right? You should notice the first item in the finger table should always be the successor. So as you can see, 130, 330, and 000. Right? 130, 330, 00. So this is our initial state. So let's see what happens if someone joins. In this case, node 6 join. The joining of this will update certain tables of other nodes. Because, for example, right, this used to be 0, because without 6, the 4 is, taken care by 0. But now, since we have 6, this one is handling 4, so this one should be 6 instead of 0. Also, 5 is for become 6, and also 4 and 5, so let's see whether we got this update. So I start here by node 6. Watch out here, see the difference has already got updated. Alright, so okay, 136, 136, 336, 336, 660. Alright, and also for 6 itself is 003. 003. Okay, cool. So second example is, what if somebody left? In this case, 1 is going to leave. Alright, so actually there's a typo here. After 1 left should be 1 3 should be responsible for 1, 2, 4. So this actually should be 336. That's a typo for the paper, but you know, it's a, well, no one paper, right? And so 3's table should be 60, and the 6th table should be 003. As you can see, there's no 1 in any table because it's gone. Alright, so let's do that. So I'm going to queue the process of 1, but you should notice, watch out here, 1 should be gone. Alright, and also those should be updated accordingly. Alright, watch out here. As you can see, 3 set its predecessor to null. Whoa, then its predecessor becomes 0. Let's see here. Alright, so it's still changing. Still changing. Still changing. Okay, now it becomes a relatively stable state. Okay, it's 336. Like I said, this is a typo, so it should be 336. 660, 660, and 003. Alright, so we have a working infrastructure of chord ring. So you can implement further if you want to do, let's say, replication to provide availability or to other interesting stuff if you want. So that's all. Thank you.